Sit down. No, actually, don't. Stand up, if you can, and put your hand flat against your chest. Feel that? That's roughly 80 kilograms of you pressing down against the floor, or 90, or 60, whatever your particular allotment happens to be. You've spent your entire life assuming you know what that weight is made of. Meat, bone, water, atoms, if you paid attention in high school. Atoms made of protons and neutrons and electrons, little solid marbles orbiting a nucleus like a tiny solar system. That picture got you through your SATs, and it will not survive the next hour. I want to be upfront about that, because I've watched this exact realization take the color out of a person's face in real time, and I'd rather you brace for it now than resent me for it later. My name is Daniel Kessler. I've spent 38 years at Stanford working on the internal architecture of matter. String theory in the early days, when saying those two words in a seminar room got you either genuine excitement or open contempt, and later the holographic principle, which is the strange idea that everything happening inside a three-dimensional region of space might be fully described by information living on its two-dimensional boundary, the way a hologram on a flat card can throw a three-dimensional image at you. I spent the better part of a decade in a running argument with a very famous colleague about what happens to information when it falls into a black hole, whether it's destroyed, which would break quantum mechanics, or preserved, smeared out on the event horizon in a way that took me years and a change of heart to accept. I lost that argument for a long time, in the sense that I was wrong about how to resolve it, and then I won it, in the sense that the physics community eventually came around to something closer to my side. I tell you this not to impress you. I tell you this because tonight's topic, what is mass actually made of, requires exactly that kind of stubborn, uncomfortable revision. And I want you to know I've done it before, and I'll do it again in front of you tonight, live, if the argument demands it. Here's the confrontation. Right up front, no runway. Almost all of the mass in your body, I mean north of 99% of it, has absolutely nothing to do with the Higgs boson. I know, you read the headlines in 2012, "The God particle explains why things have mass." Every newspaper on Earth ran some version of that sentence, and it is, at best, radically incomplete, and at worst, actively misleading about where your body's weight comes from. The Higgs mechanism is real, it's beautiful, it earned a Nobel Prize, and it is responsible for maybe 1% of the mass sitting in the chair you're not sitting in right now. The other 99% comes from something almost nobody explains properly, something that has nothing to do with a field giving particles a lazy drag as they move through it, and everything to do with pure, raw, kinetic energy trapped in a box too small to let it escape. That's not a metaphor. That is the actual physics. Stay with me, because we're going to build this from the ground up, brick by brick, and I am not going to let you skip a single step, because the shortcuts are exactly where the misunderstanding lives. Let's start where everyone starts, which is wrong, but usefully wrong, the way a rough sketch is wrong before the final painting. You were taught that an atom has a nucleus made of protons and neutrons, and that protons and neutrons are made of 3 quarks each. 2 up quarks and 1 down quark for a proton, 2 down and 1 up for a neutron. Fine so far. That part is correct. Where the picture breaks is what happens next. Because most people, if you pushed them, would guess that the mass of a proton is just the sum of the masses of its 3 quarks, the way the weight of 3 apples in a bag is the weight of apple 1 plus apple 2 plus apple 3. Let's actually do that arithmetic, because Sagan, sorry, old habit, wrong century, wrong guy, because I like doing arithmetic in front of an audience. It keeps everybody honest, including me. An up quark has a mass of about 2.2 million electron volts when you convert mass into energy units the way particle physicists do, using Einstein's famous relation. A down quark comes in around 4.7 million electron volts. A proton is 2 ups and 1 down, so let's add 2.2 plus 2.2 plus 4.7. That gives you roughly 9.1 million electron volts. Now here is the number that should stop you cold. The actual measured mass of a proton is about 938 million electron volts. 938. We were off by a factor of more than 100, not a rounding error. not experimental noise. A gap so enormous that if this were an accounting discrepancy, the auditors would be calling the police. 99% of the proton's mass, and therefore 99% of the mass in your body, since your body is mostly protons and neutrons, is simply unaccounted for by adding up the masses of its constituent parts. So where did it go? Or rather, where did it come from? Because it's not missing, it's very much there. We just didn't know where to look. Now here is where it gets strange, and I mean that in the precise, technical sense a physicist means it, not the sense a late-night television host means it. The three quarks inside a proton are not sitting there quietly, holding hands, waiting to be weighed. They are being violently, relentlessly, permanently confined by the strong nuclear force, mediated by particles called gluons, and the interaction is so powerful that empty space inside the proton is not empty at all. It is a boiling, roiling storm of virtual gluons popping in and out of existence, and virtual quark-antiquark pairs flickering into being and annihilating again, all inside a region roughly a femtometer across that's a millionth of a billionth of a meter smaller than the wavelength of visible light by a margin so large that trying to picture it with an everyday analogy will fail you, and I'm not going to insult you by pretending otherwise. What we call the mass of the proton is overwhelmingly the energy of this confined chaos. It is the kinetic energy of quarks moving at close to the speed of light, bouncing around inside a cavity they can never escape, plus the binding energy of the gluon field holding the whole system together. Mass, in this picture, is not stuff. Mass is captured motion. Mass is energy that has nowhere to go, so it just sits there, weighing something. Because Einstein told us energy and mass are the same currency, exchanged at a fixed rate, the speed of light squared, and if you trap a huge amount of energy in a tiny box with no exit, that trapped energy shows up on a bathroom scale as weight. I want to give you a thought experiment here, because I promised myself I would not let this lecture drift into abstraction without keeping at least 1 foot on physically concrete ground. Picture a sealed steel box, perfectly rigid, perfectly reflective on the inside, containing nothing but photons, particles of light bouncing back and forth off the interior walls. Individually, a photon has 0 rest mass. 0. Not small, 0. That's a hard fact of quantum electrodynamics. It is baked into the theory at the deepest level. And yet, if you put this sealed box of bouncing photons on a scale, the scale will register a weight greater than the weight of the empty box alone. Where did that weight come from? It came from the energy of the photons themselves. Trapped energy, even massless energy, contributes to the total mass of the system, because mass, in relativity, is really a statement about the total energy content of a system as measured in the frame where the system's total momentum is 0, what physicists call the rest frame. The box isn't moving. The photons inside are moving, wildly, in all directions, canceling out their net momentum, but their energy doesn't cancel. Energy is a strictly positive quantity. It just adds up, and that leftover energy, unable to average itself away, manifests as mass. That is not an approximation of what's happening inside a proton. That is, almost point for point, exactly what's happening inside a proton, except the photons are replaced by gluons and quarks, and the box is not steel, it's the confining force of quantum chromodynamics itself, a force so strange that it gets stronger, not weaker, as you try to pull the quarks apart. The opposite of gravity, the opposite of everything your intuition tells you a force should do. Let me build the second brick, because I promised you a foundation and a building, not just a foundation. Why does the strong force behave this way? Why does it get stronger with distance instead of weaker, like every other force you've ever heard of? Gravity falling off with the square of distance, electric force doing the same? The answer is a property called asymptotic freedom, and it is one of the genuinely great discoveries of 20th century physics, worked out by David Gross, Frank Wilczek, and David Pulitzer in 1973, and it earned all 3 of them the Nobel Prize in 2004. What they showed, through some of the most demanding calculations of the era, is that the coupling strength of the strong force runs, it changes with the energy scale at which you probe it. At very short distances, inside the heart of a proton, quarks behave almost like free particles, barely interacting at all, which is why early experiments smashing electrons into protons at the Stanford Linear Accelerator, right here, practically underneath the building I've spent my career in, found evidence for point-like constituents rattling around almost independently inside the proton, a discovery that won Jerome Friedman, Henry Kendall, and Richard Taylor their own Nobel Prize in 1990. But pull those same quarks apart, try to separate them, and the force between them doesn't weaken, it strengthens. And it strengthens so dramatically that at some point it becomes energetically cheaper for the vacuum itself to spontaneously produce a new quark-antiquark pair out of pure energy than to let the separation continue. This is why you have never seen a free quark, and you never will. Not in this universe, not with any accelerator we could plausibly build. Try to yank a quark out of a proton, and instead of pulling out a lone quark, you tear the fabric of the vacuum and manufacture a whole new pair of particles, a quark and an antiquark, out of nothing but the energy you were putting into the pulling. That's not a failure of our experiments. That's confinement, and it is as real and as unforgiving as gravity holding your feet to the floor. I want to pause here and tell you about the years I spent thinking about this the wrong way, because I think intellectual honesty requires it, and because I think it will help you avoid the same trap. When I was younger, still absorbing quantum field theory as a graduate student, I pictured the vacuum the way most people picture it, as a kind of neutral backdrop, an empty stage on which particles perform. Nothing there, nothing happening, until a particle comes along and does something on top of it. It took me embarrassingly long, and several very patient conversations with colleagues who understood quantum chromodynamics far better than I did at the time, to fully internalize that the vacuum inside a proton is not a stage. It is an active participant. It has structure. It has energy density. The gluon field condenses into something physicists call the quark condensate, a non-zero background value that fills all of space, breaking a symmetry called chiral symmetry. And that breaking is itself responsible for a huge chunk of the mass we're discussing. I resisted this for longer than I should have, because it felt like cheating. Mass coming from the structure of empty space itself felt like a magician pulling a coin from behind your ear. Too convenient to be the real explanation. I was wrong to resist it. The mathematics is unambiguous. It has been confirmed through an enormously demanding computational technique called lattice quantum chromodynamics, where physicists discretize space-time into a grid, imagine a four-dimensional chessboard, and solve the equations of the strong force numerically on the largest supercomputers on the planet. And the answer that comes out, again and again, independent of who runs the calculation, is that the vast majority of the proton's mass emerges from this dynamic, churning, self-interacting vacuum structure, not from the bare masses of the quarks sitting inside it. Now let's bring the Higgs back in, because I don't want you walking out of here thinking I've dismissed it, and I don't want you thinking the story is simple once you strip the Higgs away. Nothing about this is simple, and anyone who tells you otherwise is selling you something. The Higgs field does something real and irreplaceable. It gives fundamental particles, quarks, electrons, and a handful of others their bare mass, the mass they would have in complete isolation, stripped of all the strong force chaos we just spent 20 minutes building up. Without the Higgs mechanism, quarks and electrons would be exactly massless, the way photons are, and a massless electron would move at the speed of light permanently, unable to be captured into an orbit around a nucleus, which means atoms as stable structures simply would not exist. Chemistry would not exist. You would not exist. So the Higgs is not a rounding error in some cosmic accounting sense. It is a load-bearing wall in the architecture of the universe, and pulling it out collapses everything above it. What I am telling you is something more subtle and, I think, more astonishing. The Higgs gives the fundamental particles their seed mass, a small number, And then quantum chromodynamics takes that seed and, through the sheer violence of confinement, through binding energy and virtual particle churn and vacuum condensate, amplifies it by roughly 2 orders of magnitude to produce the mass of the proton, and by extension, the mass of you. You are, biologically speaking, mostly bound energy. You are a standing wave of quantum field interactions that has, for the moment, achieved enough stability to read this sentence. Let me give you the second thought experiment, because I think it will land the point even harder than the first one did. Take a hydrogen atom, 1 proton, 1 electron. Now heat it up, ionize it, strip the electron away, and consider just the proton by itself. Then imagine somehow disassembling it into its 3 constituent quarks and separating them to a safe distance, if such a thing were physically permitted, which it isn't, but let's do the accounting anyway as a formal exercise, the way physicists do all the time with idealized scenarios that can't literally happen but that illuminate real physics. The rest energy of the free, separated quarks, using their bare Higgs-given masses, is that roughly 9 million electron volts we calculated earlier. The rest energy of the bound proton is 938 million electron volts. The difference, roughly 929 million electron volts, is negative binding energy made positive by confinement. Ordinarily, in nuclear and atomic physics, binding energy lowers the total mass of a bound system, because you have to put energy in to pull the pieces apart, so the bound state sits in an energy well below the sum of its free parts. A deuterium nucleus, for instance, a proton plus a neutron bound together, weighs slightly less than a free proton and a free neutron added up separately, and that missing mass is exactly the energy released when they fused, the same physics that powers the sun. But inside the proton, the situation inverts in a way that still, after decades of studying it, strikes me as one of the strangest features of quantum chromodynamics. The energy required to confine the quarks, the kinetic energy of their relativistic motion, the gluon field energy, all of it adds up to more than the bare mass you started with, not less, because you're not looking at a weakly bound system releasing energy to reach a comfortable equilibrium. You're looking at a violently, permanently confined system where the confinement itself costs enormous energy to maintain, energy that never gets released because release would mean liberating the quarks, and the theory forbids that outright. The proton is not a well, it's a pressure cooker that never turns off. There is a mathematical structure underneath all of this that I want to at least gesture toward, because I promised you the real thing, not a cartoon. The equations governing quantum chromodynamics are a non-abelian gauge theory, built on a mathematical symmetry group called SU3. Think of it as a more elaborate cousin of the rotational symmetries you're intuitively familiar with, except instead of rotating an object in ordinary three-dimensional space, you're rotating an internal property of quarks called color charge, which has nothing to do with visible color and everything to do with a threefold internal degree of freedom that the strong force is sensitive to. The crucial mathematical feature that makes quantum chromodynamics behave so differently from quantum electrodynamics, the theory of light and electrons, is that the force-carrying particles, the gluons, themselves carry color charge, unlike photons, which are electrically neutral and therefore don't interact with each other. Gluons interact with other gluons. This self-interaction is the mathematical seed of asymptotic freedom and confinement both. It's why the force gets stronger with distance, and it's why solving these equations analytically, with pencil and paper, in the regime relevant to a proton's internal structure, has defeated every attempt for 50 years. This is, incidentally, one of the 7 Millennium Prize problems set by the Clay Mathematics Institute, proving, with full mathematical rigor, that quantum Yang-Mills theory, the general mathematical framework underlying quantum chromodynamics, has a mass gap, meaning the theory predicts a minimum non-zero mass for its excitations, consistent with everything we observe experimentally and everything our supercomputers calculate numerically, but not yet proven as a matter of pure mathematics. There is a $1 million prize sitting on a problem that is, in a very real sense, the mathematical skeleton of why your body weighs what it weighs, and nobody has claimed it. I find that thought genuinely thrilling, and I hope you do too. Now, here's where it gets strange for the second time tonight. And this is the part where I ask you to set aside your remaining intuitions entirely, because we're about to leave the proton and ask a much larger question. The question that connects tonight's topic to the deepest, still unresolved puzzles in physics. If mass is fundamentally trapped, confined energy, if what we call stuff is really just information and interaction density locked into a small enough region to register as weight, then what does that tell us about what physical reality actually is at the most basic level? This is not a rhetorical flourish. This is a live research question, and it's connected directly to the work I've spent much of my career on, the holographic principle. The idea, first proposed by Gerard 't Hooft and developed further by others, including myself, is that the maximum amount of information that can be contained within any region of space is not proportional to its volume, as you'd naively expect, twice the room, twice the information, but is instead proportional to the area of its boundary, measured in fundamental units related to the Planck length. This sounds like a strange piece of trivia until you realize what it implies. It suggests that our entire three-dimensional experience of the world, including everything that constitutes your mass, might be, at the deepest level, a projection of information encoded on a lower dimensional surface, the way a two-dimensional hologram encodes a full three-dimensional image. I do not say this lightly, and I do not say it for spectacle. This idea emerged from taking black hole thermodynamics with total seriousness, from Jacob Bekenstein's insight in the early 1970s that a black hole's entropy, a measure of hidden information, is proportional to the area of its event horizon rather than its volume, and Stephen Hawking's subsequent discovery that black holes radiate, that they have a genuine temperature, that they are thermodynamic, objects in every sense of the word. If a black hole's information content scales with area, and if black holes represent the most extreme, most densely packed concentrations of mass permitted by the laws of physics, then area, not volume, may be the truly fundamental measure of how much stuff, how much mass, how much information, how much reality a region of space can hold. If that's right, and I want to be honest with you that if is doing serious work in that sentence, then everything we discussed tonight about quarks and gluons and confined energy is itself a lower dimensional shadow of something even more fundamental happening on a boundary we cannot directly perceive. That is not a comfortable thought. It is not meant to be comforting. It is meant to be true, or at least on the road toward truth, and those are frequently not the same destination as comfort. I want to give you my honest, unresolved discomfort here, because I promised you intellectual humility and I intend to deliver it, not as a rhetorical device, but as a genuine confession. We do not know, with the kind of certainty I'd want before staking my reputation on it, how the holographic principle connects concretely and quantitatively to the mass-generating mechanisms of quantum chromodynamics that I spent the first half of this talk building for you. We have beautiful, rigorously worked out correspondences in idealized theoretical settings, the ADS/CFT correspondence, developed by Juan Maldacena in 1997, which precisely relates a gravitational theory in a curved, negatively curved spacetime to a quantum field theory living on its boundary, a theory that, in some mathematically controlled limits, closely resembles quantum chromodynamics. That correspondence has been one of the most productive theoretical tools of the last 3 decades, and it has genuinely illuminated aspects of strongly coupled gauge theories that we couldn't access any other way. But our actual universe is not negatively curved in the way that correspondence strictly requires. It's very close to flat, with a small positive cosmological constant, and translating the holographic principle cleanly into our real, physical spacetime remains unfinished business, an open wound in the theory that keeps me up more nights than I'd like to admit at this point in my career. I have spent decades on this, and I do not have it fully resolved, and I think you should be deeply suspicious of anyone standing on a stage who tells you they do. Let's come back down to earth, because I don't want to leave you floating in abstraction without giving you the full weight, so to speak, of what we've built tonight. When you stand on a scale tomorrow morning, The number staring back at you is not primarily a measure of quark mass, and it's not primarily a triumph of the Higgs field, however much the newspapers wanted that headline in 2012. It is, overwhelmingly, a measure of confined kinetic energy and gluon field-binding energy, locked inside roughly 10 octillion protons and neutrons distributed across your body, each one a tiny, permanent, inescapable storm, a pressure cooker running at full boil since roughly a microsecond after the Big Bang, when the universe cooled enough for quarks to become confined into hadrons for the very first time, a phase transition called the quark-gluon plasma transition, which experiments at the relativistic heavy ion collider at Brookhaven and later the Large Hadron Collider at CERN have actually recreated, briefly, by smashing heavy nuclei together at speeds close to light, generating temperatures in excess of 4 trillion degrees, hot enough to momentarily melt protons and neutrons back into their constituent quarks and gluons, into the same free-flowing plasma that filled the entire universe for those first few millionths of a second. You are made of matter that briefly forgot how to be matter, cooled, condensed, and has been trapped in that confined state for 13.8 billion years, holding its shape well enough to become stars, then heavier elements forged in the collapsing cores of dying stars, then planets, then, eventually, through a chain of chemistry so improbable that I still find it faintly astonishing every time I think about it carefully. I've spent most of my career being wrong in interesting ways before eventually being right, or right enough, and I think that's the honest state of the science on this exact question, too. We are right that the vast majority of visible mass in the universe comes from confined energy rather than fundamental particle mass. That part is settled, confirmed to remarkable precision by lattice quantum chromodynamics calculations that now agree with experimentally measured hadron masses to within a percent or two, which is, frankly, one of the great quantitative triumphs of theoretical physics in my lifetime. We are less settled, far less settled, on how this picture connects to gravity, to the holographic structure of space-time, to why the vacuum energy of the universe, which ought to be enormous, given all this churning quantum field activity we've spent an hour discussing, is instead almost, but not quite, exactly zero, a discrepancy between naive theoretical prediction and cosmological observation that runs to something like 60 orders of magnitude and remains, by a wide margin, the worst quantitative failure in the history of theoretical physics. I don't say that to depress you. I say that because it's true, and because it means the conversation we've had tonight isn't a closed chapter in a finished textbook. It's the current working edge of a live investigation, and some of you in this room, right now, are young enough and stubborn enough to be the ones who eventually crack it. So here is what I want you to carry out of this room. And I want to be precise about it, because precision is the only kind of respect I know how to pay an audience. You are not made of little solid balls of stuff. You never were. That was always a convenient fiction. A scaffold to get you through introductory chemistry so you could later tear the scaffold down and see the actual building. What you are made of is confinement, energy that cannot escape, motion that has nowhere to go, a churning quantum vacuum condensing into structure stable enough to fall in love, write poetry, argue about black holes, and occasionally stand in a room and listen to a stranger try to explain why the floor beneath your feet is pushing back against roughly 99% pure trapped energy and 1% something. We're still, honestly, working out how to fully connect to the rest. The universe did not have to build mass this way. It could have been a simpler story. Particles with fixed, God-given weights, full stop, nothing more to say. It chose instead to build almost everything you love and everything you are out of a violent, unresolved argument between quarks that can never stop moving and a force that will never let them go. I don't know a more honest description of what it feels like to be alive than that. And I don't know how to leave you with a neater ending, because there isn't one. There's only the next question, which is what happens to that confined energy, that trapped information at the boundary of a black hole where everything we've discussed tonight and everything I've spent my career arguing about collide, head on. And I promise you, We have not finished that argument, not by a long way, and neither should you.